All right, so we have come to the grand finale, as it were, for power series, well, for infinite series in general, but power series in particular, and talking about Taylor and Maclaurin series. So in the last lecture, we were talking about power series, and in particular, how we can create power series representations of functions. If you remember, we looked at a particular power series whereby we saw that it was equal to the function 1 divided by 1 minus x. We basically got that from the geometric series. And from that, we were able to replace x with different values and create power series representations of other functions. And then we looked at how to do term-by-term differentiation and integration of power series, and thereby constructing power series for other types of functions. And what we're going to do now is develop general methods for finding a power series representation for any function. Now, the function will have to have derivatives of all orders. What this basically means is that we have a first, second, third, fourth, etc. Derivative for the function. In that case, we are interested, right, in finding a power series representation here. Let's suppose, again, we're centered about A with an interval of convergence, right, which, depending on the situation, again, we may or may not include these endpoints. Remember that. We may or may not include these endpoints. But the radius of convergence is some finite, or it could be infinite, in which case, right, we would not have to check the endpoints. It would be convergent for all real numbers of x. And so here's the general form for a power series. And so our task is for a given function to find the values of these coefficients. All right. So the big task is, what are these c sub n's? Right. You've got c sub 0, c sub 1, c sub 2, and so on. They're functions of n, right? As n varies from 0, increments by 1 each time, right? Then we're getting a new expression. The x minus a to the n, that's going to be fixed, right? Depending on the value of a, what we're centered about. X is the variable, and we're just going to get x minus a squared, x minus a cubed, and so on. So the real question is, what's that coefficient? And so here's what we're going to do. Do a little pattern recognition here. I'm going to start with this power series, right, with this radius of convergence, and I'm going to do term-by-term differentiation to find f prime of x. And I'm going to get a power series representation for f prime of x. So let's just term-by-term differentiate. Remember, the c sub n's in terms of, with respect to x, are constants, right? They're functions of n, but when we take the derivative with respect to x, they're constants. So c sub 0 is a constant. Derivative is 0. What's the derivative of c1 times x minus a? Well, it's just going to be c1, right? This is c1x minus a times c1 if I distribute. But the derivative of c1x is just c1. The derivative of c1 times a is 0 because it's a constant. And then here, what do? c2 is a constant multiple. Bring the 2 down, times x minus a to the first. We got a little chain rule, but again, the inner function x minus a, its derivative is just 1. And so the derivative here is 2c2 x minus a to the first power. Derivative here is what? Bring the 3 down. 3c3 x minus a, 3 minus 2 second power. All right. What will the next one be? Even though I don't have it here, you should be able to guess what that's going to be. It will be c sub 4 x minus a to the fourth. So that's going to be what? 4c sub 4 x minus a cubed, and ... right? So you see that pattern developing. And the radius of convergence for this power series is still this, right? This is still the same, right, from what we learned last time. Okay? So let's continue. Let's find a power series representation for the second derivative of our original function. Now I'm taking the derivative of these, right, terms. All right? The derivative of c1 is 0 because it's a constant. What's the derivative of this thing going to be? It's just going to be 2c2, right? because 2c2 times x, the derivative is 2c2x, and 2c2 times a is just a constant. Over here now I've got bring the 2 down, 3 times 2, 6c3x minus a. I know that's 6, but let me just go ahead and write that as 3 times 2 c sub 3 x minus a to the first power. Yeah, that's 6. I understand that's 6, but I'm going to be looking for a little pattern recognition, and so I want to do it this way. So here I'm going to bring down the 3, 4 times 3, which of course is 12, c sub 4 x minus a squared. What would the next one be here if I had to do that one? You know what? Can you see a pattern developing here? I mean, you can think about what that next term is going to be. What's it going to be? It's going to be 5 times 4 c5 x minus a cubed. Now, and then that continues. Okay. So pattern recognition here. Let's go to the third derivative. Derivative of a constant is 0. What's the derivative of this thing going to be? Just 3 times 2, 3 times 2 c3. Is that the same as 3 times 2 times 1 c3? Yeah. Why would I do that? Well, let's see here. What is that really? 3 times 2 times 1. Isn't that what? 3 factorial times c3? Yeah. What's happening over here? I get plus 4 times 3 times 2. Now bring the 2 down. c4x minus a to the first. What's here? Bring the 3 down. 5 times 4 times 3 c5x minus a squared, and so on. Let's do a couple more. The fourth derivative. Now, instead of writing 4 tick marks as you get higher order derivatives, you'll have too many tick marks. Typically, if you remember, you can put in parentheses the order of the derivative. This is the fourth derivative. It's not the fourth power. If you put parentheses around the superscript here, that means the fourth derivative of the function. If it's without the parentheses, it would be the function f, the original function, raised to the fourth power. But this is the fourth derivative of the function. The fourth derivative of the function. This is all constant. The derivative is 0. This is what? What's the derivative of this? It's just 4 times 3 times 2 times 1 c sub 4. But 4 times 3 times 2 times 1 is just what? 4 factorial times c sub 4. Plus what? What's the derivative of this? Bring the 2 down. 5 times 4 times 3 times 2. C sub 5 x minus a to the first power now. What's the fifth derivative going to be? Derivative of a constant. All right, that's a constant with respect to x. This has an x, but this will be what? 5 times 4 times 3 times 2 times 1. 5 factorial c sub 5 plus and so on. Okay, so notice the plus dot 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 here. All these terms will still have an x minus a factor. This first one will have x minus a factor. The next one x minus a squared, and so on. Right? Each factor is, if you think about it, as we differentiate, x cubed then becomes x squared, then becomes x minus a to the first, and then becomes a constant as we're going down this list. What do you see a pattern though? Because you've got 5 factorial c sub 5 here, 4 factorial c sub 4, 3 factorial c sub 3. 2 is the same as 2 factorial, isn't it? And what's 1 factorial? 1, right? So you see 1 factorial 1. You see this constant term coming out. Let's just go to the sixth. What's it going to be? The sixth derivative of the function. It's going to start out with what? 6 factorial c sub 6, right? And then, an infinite number of other terms that have an x minus a factor in them. So, the question to us is the following. what's the general nth derivative if this pattern continues? Do you see the pattern? What's the pattern going to be? If it's 4, it's 4 factorial c sub 4 plus a bunch of stuff. Fifth derivative, 5 factorial c sub 5 plus a bunch of stuff. Sixth derivative, 6 factorial c sub 6 plus a bunch of stuff. So this is obviously going to be what? N factorial c sub n plus a bunch of stuff. And I'll just have you note that this stuff, these each have a factor of x minus a. Right, so you each have a factor of x minus a. It's either x minus a, or x minus a squared, or x minus a cubed, and so on, right? All the way to, this goes on forever, right? All those have a factor of x minus a. Okay. So here's the neat thing now. Here's the neat thing. Here we go. What is the nth derivative of our function evaluated at a? Evaluated at x equal a. Remember, this original power series was centered about a, right? So let's say what is the nth derivative evaluated at a? Well, if each of these, so if we plug in, there's no value of x for this. Each one of these have a value of x, but every time I plug in x, what happens? I would plug in rather a for x. What happens? A minus a, 0. Right? This factor becomes 0. And since each one of these infinite number of terms has this factor, when I evaluate it at a, they all go to 0. And all I'm left with is n factorial times c sub n. Do you remember what we were doing in all this? Well, that's a lot of stuff. What were we doing? Let's go back to the beginning. We were doing what? What are the c sub n's? What are these coefficients? C sub n's. What are they? What are they? They're right here. Can I solve for the c sub n's? Yes. Divide both sides by n factorial. Here is your answer. There it is. This is a formula to generate the coefficients of a power series. For any function, you do need to be able to find its derivatives, right? First, second, third, and fourth. And in general, you really need to see if you can come up with a formula for the nth derivative of the function, evaluate it at a, and then just divide it by n factorial, and that will be your c sub n's. Now, finding a general formula for the nth derivative of a general function might be a little tricky. Okay, so we're going to spend some time looking at that. But we've informally showed how to find these coefficients. Let's give the formal definition and give credit to the individuals who did a lot of work in this area, namely Brooke Taylor and Colin Maclaurin. These were the mathematicians and did a lot of work in this area. And so, if a function is represented by a power series, and we're going to call that power series t of x, and you'll see why we call it t of x in just a minute, centered about x equal a with an interval of convergence again, radius of convergence greater than 0, then the power series t of x is called a Taylor series. So this is in honor of the British mathematician Brooke Taylor, who formally introduced the concept. And so here's the Taylor series. You'll now see what I have done, right? The c sub n's we found to be what? F, the nth derivative of the function f at a divided by n factorial. There's the c sub n's. That's all I've done is replace the c sub n's with that. There's the actual Taylor series. It is a power series still, right? And here's all the expanded version of that. Now, there was also this thing called a Maclaurin series. Well, in the special case, when a is equal to 0, in that special case, when we're talking about finding a power series representation for a function centered about 0, right, then the Taylor series we typically will call a Maclaurin series. And this is in honor of Colin Maclaurin, who made extensive use of the special case back in the 18th century, in the 1700s. So, here's the special case, right? Maclaurin series. Just really, Maclaurin series are Taylor series. Now, Maclaurin series is a little bit easier to find because when you plug in 0 into something, it's just easier to deal with in a lot of ways. Okay. So again, the trick to finding a Taylor series or a Maclaurin series is to see the pattern of these coefficients, to be able to, if you can write this as an explicit function of n, then you've got it. But that's the tricky part. Okay. Well, let's start easy. We'll start with Maclaurin series because they are easier where they're centered about 0. And we're going to do this one for the function e to the x, which is a pretty easy function to deal with. So we're going to go again about what? Since it's Maclaurin, we're going to go about a equal 0. And so our power series looks like this. X minus a, x minus 0 is just x to the n. And again, where's our c sub n's we know are the nth derivative evaluated at a, which is 0 in this case, over n factorial. Okay, so again, it's just pattern recognition. We'll start with the original function. Let's just say this, that what is this? If I say f, the 0th derivative of the function, what is that? Well, that's what we mean by the original function. If you ever see the 0th derivative, that's just the original function. It's not f to the 0 power, so it's not 1, right? It's the original function, which is just e to the x. And so in particular, f0, the 0th derivative of the original function evaluated at 0 is e to the 0, which is 1. And I need to evaluate it at 0 here. Okay? Well, what's the first derivative of our function? F prime of x. Well, that's also e to the x, right? Derivative of e to the x is e to the x. So the first derivative evaluated at 0 is e to the 0 is equal to 1. Well, what about our second derivative? E to the x as well, right? And therefore, what's the second derivative evaluated at 0? It's also 1. Okay? What's the third derivative going to be evaluated at 0? 1. And see, what's the nth derivative at 0 going to be? 1. This pattern is pretty darn easy to recognize, right? 1, 1, 1, 1, 1. What's the pattern? 1. It's always 1. This is the easiest Maclaurin series there is to find. So our c sub n's, right, are equal to what? What is this? What is the nth derivative evaluated at 0? It's always 1, right? Over what? N factorial. That's our coefficient. And so the Taylor series for our function is 1 over n factorial times x to the n. Sorry, I was writing off the screen there. 1 over n factorial x to the n. Or we can write a little more compactly as just, whoops, can't write my sigma sign very well here, x to the n over n factorial. And if you go back in when we introduced power series and term-by-term differentiation, we looked at this power series, did term-by-term differentiation, and we realized, hey, it's the same. We get back to the original function. And I asked you at that point, what function was it? If you said e to the x, then give yourself a pat on the back. That's pretty darn good, because that's exactly the function we're talking about. So this is the Maclaurin series for e to the x. Okay, so there's a nice start. We are going to, in the next video, look at a little more complicated situation, and then we will look at a Taylor series, or a Maclaurin series rather, for sine of x. Yeah, let's take a look at that in the next video.